In this video, we're going to study the simplest type of beam under bending, the Euler-Bernoulli beam. Beam structures are those structures whose length is much longer than the cross-sectional dimensions. Using certain assumptions on the deformation of the cross-section, the equilibrium equations for a beam can easily be solved. For an Euler-Bernoulli beam, there are three basic assumptions. The first assumption is that plane sections perpendicular to the neutral axis of the beam before deformation stay plane and perpendicular to the neutral axis after deformation. Usually in beams, we also assume the deformations are very small. Also, the third assumption is that the beam is usually made out of linear, elastic, isotropic material, and usually, for simplification, Poisson's ratio effects are ignored. The first assumption allows us to imagine what the deformation of the beam would look like. We said that the first assumption is plane sections remain plane and perpendicular to the neutral axis, and the neutral axis is actually the geometric centroid of that beam. So, if we have vertical lines representing the sections of the beam, after deformation in an Euler-Bernoulli beam, these stay perpendicular to the neutral axis and they stay as plane. In order to calculate the displacement of the beam, we're going to track a point with coordinates x1p, x2p, and x3p. So basically we want to see where the point with the black dot goes after deformation. And we assume that the neutral axis has deformed by a function y, the displacement y, where y is a function of the horizontal position on the beam. Given that this distance is y, then the new position of the point can be calculated knowing that plane sections remain plane and perpendicular. So the new coordinates of this point are equal to the vertical component is equal to the original component minus x2 sine theta, while the vertical component is equal to the distance y plus x2 cosine theta, where theta is the inclination of that cross section. And so this basic assumption of plane sections remain plane and perpendicular to the neutral axis after deformation allows me to calculate the position of the point after deformation being or having those three components. So, given capital X as the original position, small x as the new position, the displacement is equal to x minus capital X and gives me those three components. The second assumption, small deformations, because we are assuming that the deformation is very small, theta was the rotation of the cross section, we can assume that the rotation is very small. Sine theta can be assumed to be equal to theta, can be assumed to equal to tan theta, which is equal to y prime. Cosine theta, on the other hand, can be assumed to be equal to 1. And in that case, the displacement after using these assumptions will be equal to x minus x, and we're going to be left with only in the vertical component will be negative x2 sine theta. Sine theta is equal to y prime, which is dy by dx1. Cosine theta is equal to 1, so this cancels that, and I'm only left with y. The gradient of the displacement, which is partially u1 by partial x1, partially u1 by partial x2, and so on, can simply be calculated from this displacement vector. And the small strain matrix, as usual, it's half the gradient of u plus the gradient of u transpose, which results in this equation that shows that the strain has only one non-zero component. All the other remaining strains are 0. So, we end up with the non-zero strain component epsilon 1 is equal to negative x2 multiplied by d2y by dx1 squared. This means that the strain is a linear function of x2. Epsilon 1 is function of x2. when x2 is 0, when x2 is on the neutral axis or the centroid of the cross section, epsilon 1, 1 is 0. As we go up, epsilon 1, 1 is negative. As we go down, epsilon 1, 1 is positive, and it has a linear distribution. Using the third assumption, linear elastic materials, and ignoring Poisson's ratio, sigma 1, 1 is equal to E epsilon 1, 1. And so, sigma 1, 1 will also have a linear distribution with compression on the top and tension on the bottom and 0 at the neutral axis. For beams, instead of looking at the stresses, we like to integrate the stresses over the cross-section and obtain the internal force acting on the whole cross-section. The moment around x3, this is x3, the moment around this axis is obtained by integrating the stress multiplied by negative x2 multiplied by area, and substituting that sigma 1, 1 is equal to E epsilon 1, 1, which is equal to negative ex2 d2y by dx1 squared. With this substitution and integration, we obtain that the moment is on the cross section is equal to ei multiplied by the second derivative of y, d2y by dx1 squared. Therefore, the relationship between sigma 1 and the moment is that sigma 1 is equal to negative the moment acting on the cross section multiplied by x2, the vertical distance of the point, divided by I, where I is the moment of inertia of the cross section. The next step to develop the beam equations is to find the equilibrium equations, and to do so, we're going to assume that there is a distributed load Q acting on the beam, and usually we assume that it's acting upwards, and then we're going to extract a small sliver of the beam and look at the forces acting on that small sliver of the beam. On the left, we're going to assume that the shear force is acting upwards, V. On the right, we're going to assume that it's acting downwards, V, plus partial V by partial x multiplied by delta x, and here delta x is dx1. The moment on the left is equal to m3. The moment on the right is equal to m3 plus a little bit more, and this little bit more is partial m3 by partial x1 multiplied by dx1. Summing the forces in the vertical direction and equating the forces in the vertical direction to 0, you'll get that partial v by partial x1 is equal to this distributed load Q. Similarly, taking sum of moments and equating it to 0, you'll find that partial m by partial x1 is equal to v. Because we only have one variable, which is x1, instead of taking partial derivatives, we can take the total derivatives. So dv by dx1 is equal to q, the distributed load, and dm by dx1 is equal to v, which is the shearing force acting on the cross section. Combining these equilibrium equations with the equation m is equal to ei, the second derivative of y with respect to x1 squared, allows us to write the differential equations in terms of the unknown displacement y. And so we reach the equilibrium equation in terms of the displacement that says ei d4y by dx1 power 4 is equal to q. This is an easy equation to solve and requires 4 boundary conditions to fully solve for the displacement function y. And so the solution of this equation, ei multiplied by y, is equal to the integral of q 4 times, plus a constant 1 cx1 cubed over 6, plus another constant c2 x1 squared over 2, plus c3 x1 plus c4. To find those 4 constants, we need 4 boundary conditions. The boundary conditions can be given in terms of either the displacement, the rotation, the shear, or the moment. The shear is the third derivative of y, and the moment is the second derivative of y. So any of these values, in addition to y and the first derivative of y, which is the rotation, any of these can be used as a boundary condition for the beam. Once we find the function y, we can then find the stress matrix at every point in the beam. The stress matrix at every point in the beam is given by the equation sigma is equal to sigma 1 is equal to negative m x2 over I, and the shear stress is equal to negative VQ over IB. And the proof of negative VQ over IB, you will find it in the notes online. The remaining components of the stress are 0. The strain is only equal to, epsilon 1 is the only non-zero strain, and it's equal to negative x2, so the second derivative of y with respect to the x1 squared. And you would notice that there is a little bit of discrepancy here, because we have a shear stress, but we don't have any shear strain. And this is just an approximation of the stresses, and this assumption is valid for beams with very small deformations. The term Q that appears in the shear equation can be evaluated as follows. If I would like to know what the shear stress is at this particular point, I look at the part of the cross section that is above it and calculate the area multiplied by y bar, where y bar is the distance from the centroid of that area to the centroid of the cross section. So Q is equal to area multiplied by y bar. The area in this case for a rectangular cross section is equal to the width b multiplied by the height of that cross section, which is equal to this term. And y bar is the distance from the centroid to the centroid of the area, which is equal to t over 4 plus x2 over 2, where t is the height of the beam. We're going to go through this example in class, so I'm going to present it here as well. We're going to look at a cantilever beam with Young's modulus of 20 gigapascal. The beam is 5 meters long and has a rectangular cross section. The height of the beam is 0.5 meters and the width is 0.25 meters. A load of 125 kilonewton is applied downwards at the free end. We want to draw the contour plots of sigma on 1, sigma on 2, and sigma von Mises along the beam. Also, we want to sketch the principal stress directions at the top fibers, the bottom fibers, the neutral axis, and at quarter of the height of the beam at the support. We also would like to draw the vector plot of the displacement of the beam. To solve these problems, first I need to solve the differential equation, calculate m, the moment, and v, the shear force, then calculate the stresses. This is a sketch of the beam. The equilibrium equation of the beam is EI d4y by dx1 power 4 is equal to q. In this example, q is equal to 0, and so y is equal to c1x1 cubed over 6 plus c2x1 squared over 2 plus a constant c31x1 plus a constant c4. To find these constants, I need to use the boundary conditions given in the problem. Right on this end, the displacement is 0 and the rotation is 0. And on the other end, the shear is given by EI d3y by dx1 cubed, which is 125, and the moment is given as 0. Incorporating those boundary conditions, we get that the displacement is equal to negative 125 divided by 6EI multiplied by 3L x1 squared minus x1 cubed. The moment is equal to EI, the second derivative of y with respect to dx1 squared, which is equal to this, while the shear is equal to EI, the third derivative of y with respect to x1 cubed, which is equal to this value. The stresses, sigma on 1 is equal to negative mx2 over I, sigma on 2 is equal to negative v multiplied by q divided by IB. And q was given in the slide a few slides ago. The moment of inertia I is equal to b multiplied by t cubed over 12. So now, because we have sigma on 1 and sigma on 2, we can plot the contour plots of both, and you can see, as expected, in this cantilever beam under bending, you get sigma on 1 in tension at the top fibers here, and sigma on 1 is compression at the bottom fibers here, and on the top fiber and the bottom fiber decrease as we go towards the free end. The shear stress, on the other hand, is maximum at the neutral axis and goes to 0 at the top fiber and 0 at the bottom fiber. Using the equation for the sigma von Mises, knowing sigma on 1 and sigma on 2, we can calculate sigma von Mises on the beam, and you'll find that the distribution shows the maximum sigma von Mises is at the top and bottom fiber, close to the support, where sigma on 1 is maximum. In order to calculate the principal stresses close to the support for the beam, I'm going to substitute the values of x1 and x2 depending on the particular point. For the top fiber here, x1 is equal to 0 and x2 is equal to 0.25 meters. When I substitute for sigma on 1 and sigma on 2, I will get that the stress matrix is 60, 0, 0, and everything else is zeros. And so at this particular point, I have a principal stress of 60 and the other principal stress is 0. For the next point, where x1 is 0 and x2 is equal to quarter the height of the beam, 0.125 meters, you'll find sigma on 1 to be 30 and sigma on 2, with this shear, is equal to negative 1.125. Calculating the eigenvalues and the eigenvectors of this matrix, you'll find that sigma 1 is equal to 30.042 and sigma 2, which is the second principal stress, is equal to negative 0.043. And the orientation of the eigenvectors is shown here. This is the orientation of the maximum principal stress, and this is the orientation of the second principal stress of value negative 0.043. At the centroid of the cross section, x1 is equal to 0 and x2 is equal to 0 at this point. Substituting x1 and x2 equal to 0, you'll get that sigma on 1 is 0, sigma on 2 is equal to negative 1.5. The orientation of the principal stresses is at 45 degrees, and the values are 1 is 1.5 in tension and the other one is negative 1.5 in compression. And so on. The next point, x1 is equal to 0 and x2 is equal to negative 0.125. Substituting, you'll get these values for the stresses and these values for the principal stresses. Finally, the last point, x1 is 0 and x2 is negative 0.25. The stress matrix has this form and the principal stresses are negative 60 and 0. And the orientation is negative 60 in this direction and 0 in the vertical direction. Now I will show you how to solve a problem like this using Mathematica. First, you can clear all the variables that you're going to use for this problem. Y is a function of x. I just put it here for setting it up as the variable that I'm looking to solve for. Theta, the rotation of the cross section, is equal to d y of x with respect to x. The shear is equal to ei, the third derivative of y of x with respect to x. M is equal to ei multiplied by the d y of x with respect to x twice, the second derivative of y with respect to x. The end variables, which are the boundary conditions, can be defined as follows. M1 is the moment when x is 0. M2 is the moment when x is L. V1 is the shear when x is 0. V2 is the shear when x is L. Y1 is the y of x when x is 0. Y2 is y of x when x is L. Theta 1 is theta when x is 0. And theta 2 is theta when x is equal to L. The next step is to solve the differential equation. You can use the function dsolve. The differential equation is ei, the fourth derivative of y, double equal 0. The boundary conditions are the moment at the second end is equal to 0, m2 equal 0. The shear on the second end was equal to 125. y1, the displacement of the first point was 0, and theta 1 was equal to 0. So this is the differential equation and the boundary conditions. They're all between a set of curly brackets. We need to solve for y as a function of x. And after solving for y, we need to store this solution in the variable y. So we say y is equal to this function y of x when I use the solution. After calculating y, we can now set our values. Ei is equal to Young's modulus multiplied by the moment of inertia, and I'm using capital EE for Young's modulus and capital II for the moment of inertia. This is the value of Young's modulus given in the problem. This is the width of the cross section, the length, the thickness, and the moment of inertia, which is bt cubed over 12. And these are the equations for S11 and S12. This is the equation for Q. So solving for all these, and the stress matrix is equal to S11, S12, S12, and everything else is zeros. We can then evaluate the stress matrix at different points. So first point is evaluating the stress matrix when x is 0 and x2 is equal to negative 0.25. Here I'm using small x for capital X1 in the problem. And then we can calculate the eigensystem of stress matrix 1 and so on. And so you can see here, for the first case, the eigenvalues are negative 60,000, 0 and 0, and the eigenvectors are these three. And for the second case, this is the answer, which was shown in a few slides ago. And so on, you can evaluate the stress matrix at any point with any coordinates as you wish.